Assalamualaikum and hi everyone. So this video is where my group, which is group 3, will present about our problem assignment. This is my group mate, Amni, Dina, Nurin, Fatin, Natasha and I, Awni. Straight to our question, we got radioactive decay. We have to solve the radioactive decay equation, which is dn over dt equal to negative lambda n, where lambda is the decay constant. Our goal is have to implement the numerical methods to calculate the remaining quantity of a radioactive substance over time. For the problem assigned, we have to use 3 methods to solve the radioactive decay equation. First, Runge-Kutta fourth-order method. Second, Adam-Bashford fourth-order method. And last, Adam-Moulton fourth-order method. From the calculation, the error was analyzed for each method. Each of error of the method is compared with the exact solution and it is shown in graph and table. So, this is graph and table for Runge-Kutta method. Next, this is graph and table for Adam-Bashford method. And last, the graph and table for Adam-Moulton method. Based on these 3 methods, the Runge-Kutta's error is very small, so this method is very accurate rather than Adam-Bashford and Adam-Moulton. As for this presentation, we have to choose one method to explain. So we choose Runge-Kutta as the method that we will explain for the problem assigned.
I will proceed with the calculation of 2 iterations of Runge-Kutta method. So the initial value of n naught will be equal to 100 and the decay constant lambda is equal to 0.144. The time step t will be equal to 1. So we will find out the first iteration where t0 to t1. First, we find the k1 time step times dn over dt and not t0. So 1 times negative 0.144 times 100, we will get negative 14.4. The next, we will calculate the k2, where time step times dn over dt and n0 plus 0.5 times k2 t0 plus 0.5 times step. So the calculation will be 1 times negative 0.144 times 100 plus 0.5 times negative 14.4. We will get the k2 will equal to negative 13.3632. For the k3, we will get 1 times negative 0.144 in the bracket 100 plus 0.5 times negative 13.3632. And we will get that k3 will be equal to negative 13.4378496. And we proceed to calculate the k4, where 1 times negative 0.144 in the bracket 100 plus negative 13.4378496. We will get the k4 will be equal to negative 12.464966. We will proceed to find the n1, where to find n1, we will calculate the n0 plus in the bracket k1 plus 2 times k2 plus 2 times k3 plus k4 over 6. So n0 is 100 plus in the bracket of negative 14.4 plus 2 times negative 13.3632 plus 2 times negative 13.4378496 plus negative 12.46494966. Alright, so we'll get the n1 equal to 86.4. We will get the n1 equal to 86.58882519. So we get the n1, the answer of n1, and we proceed to do the second iteration where t1 to t equal to 2, where the initial value of n1 equal to 86.58882519, and the lambda, the value of decay lambda is 0.144, and the time step is equal to 1. So we find the k1 of the second iteration, we will get negative 12.46879083. And for k2, we will get negative 11.57103789. And the k3 will be equal to negative 11.635671. And the last one, we calculate for the k4, we get negative 10.79325347, and we find the n2, where n2 equal to n1 plus k1 plus 2 times k2 plus 2 times k3 plus k4, where N2 equal to 86.58882519 plus in the bracket negative 12.46879083 plus 2 times negative 11.47103789 plus 2 times negative 11.63566761 plus negative 10.79325347, and it will divide it by 6. And the last one, we will get the N2 is equal to 74.97624648. And the final results after the first iteration N1 equal to 86.588825, and the second iteration N2 is equal to 74.976246.
Moving on to the next part of the method, we are going to look into the algorithm of the Runge-Kutta method. Firstly, for the initialization, set the initial condition for the N naught. Next, define the decay constant lambda, time step size h, and the total simulation time. Lastly, initialize the arrays to store numerical solution and time values and compute the total number of steps by using the following formula. As for the Runge-Kutta iteration, for each time step n, perform the following formula to compute the time. Tn equal to T0 plus n time h, where h is the time step size. Next, evaluate the derivative at the current state using the given function dn over dt equal to negative lambda times n. To find the value of K2, K3, K4, compute the intermediate derivatives by using this formula, and then update the value by using the weighted average of the slopes formula. Lastly, for the output, store the computed values of n and t in their respective arrays. Optionally, compute the exact solution for nt by using this formula, and exact t equal to n naught times exponent to the power of negative lambda times time. Lastly, perform the error analysis by using the error formula.
To implement the algorithm that have been presented just now, we use MATLAB programming code. And firstly, we define the decay constant, which is 0.144. Next, we define the exact solution, and then we define the derivative function for radioactive decay. And for the initial conditions and parameter, we use n naught equal to 100, t naught equal to 0, the final time until 20, and the time step equal to 1. And this is for the initialization. For the Runge-Kutta iteration coding, first we will calculate numerical solution using Runge-Kutta method, and then we will calculate exact solution. After that, we will perform the error analysis. After the declaration, we will visualize RK4 and exact solution. Also, we will be visualize error analysis in a separate vehicle because these visual coding are the one that will be lead to the output of the graph. And the next step is display the results in table. For the output coding, the function must be placed after the main script. And by this coding, we will get the K1, K2, K3, and K4.
Numerical methods play a crucial role in various scientific and engineering fields. Here are real-life applications of three prominent numerical methods, which are Runge-Kutta, Adam Bashforth, and Adam Moulton, in the context of radioactive decay. These methods are vital in nuclear medicine, archaeology, and environmental science. Let's explore their applications in detail.
Okay, so first off, let's talk about the Runge-Kutta method. Okay, as for the Runge-Kutta method in the terms of radioactive decay, there are two fields that we can observe. So the first one is nuclear medicine. Okay, so the knowledge of radioactive decay is essential to the safe handling and application of radioactive isotopes in cancer treatment and diagnostic imaging. To ensure the patient safety and the treatment effectiveness, the precise modeling of this degradation process aids in establishing the right dosage and timing for treatments. In addition, radioactive isotopes such as technetium-99m and iodine-131 are employed in cancer treatment and diagnostic imaging. Okay, as for archaeology,
The method of radiocarbon dating is based on the idea of radioactive decay. So, scientists can determine the age of fossils and ancient artifacts by calculating the quantity of carbon 14 that is still present in an archaeological sample. Okay, next off is the Adam-Bashforth method. Okay, as for the Adam-Bashforth method, in terms of radioactive decay, there are two fields that we can observe, which are environmental science and nuclear medicine. Okay, so first let's talk about environmental science. As for in environmental science, this method can be used to stimulate long-term radioactive decay of contaminants in groundwater or soil. Other than that, it can also be used to estimate the movement and concentration of radioactive isotopes in ecosystem over time. The Adam-Bashforth approach also aids in forecasting variations in neutron flux and decay products throughout reactor operations, which is relevant to nuclear reactor safety. Okay. It also is in the design of control systems that preserve reactor stability. Next is the nuclear medicine, which is the decay rates for isotopes in brachytherapy and other radiation-based therapies can be predicted using this method, other than Rungakuta. Okay, so moving on to the next method, which is the Adam-Moulton method. This method is crucial for applications where position and stability is highlighted. Okay, so first, it can be used to predict long-term decay processes in nuclear waste repositories, which is relevant to radioactive waste management. So other than that, it can also be observed in two fields, which are space exploration and nuclear medicine. So in space exploration, radioisotope thermoelectric generators, or also called as RTGs, which power spacecraft for extended missions, can use it to control the decay rates of isotopes. Okay, so thus, it ensures reliable energy predictions over mission durations. And as for nuclear medicine, Adam-Moulton method can also provide precise dose planning for treatments involving isotopes with complex decay chains. Additionally, uh, it incorporates feedback mechanism to improve therapy efficiency and decay forecast accuracy. I guess that's all from us, so thank you for listening.